GIS Fundamentals, Section 12, Spatial Estimation, Interpolation, Prediction, and Core Area Delineation. Spatial prediction methods are used to estimate values at unsampled locations. Predictions are required because time and money are limiting. There is an infinite number of potential sampling locations for any continuous variable in any study area, and it is impossible to measure at all locations. While there is a finite number of discrete objects in all studies, there are usually too many to measure them all. Practical constraints usually limit samples to a subset of possible lines, polygons, points, or raster cell locations. Spatial interpolation is the prediction of variables at unmeasured locations based on a sampling of the same variables at known locations. Most interpolation methods rely on the nearest points to estimate missing values, and use some measure of distance from known to unknown values. Spatial prediction also involves the estimation of variables at unsampled locations, but differs from interpolation in that estimates are based at least in part on other variables, and often on a total set of measurements. We may use elevation to help estimate temperature because it is often cooler at higher locations. A core area is characterized by high use, density, intensity, or probability of occurrence for a variable or event. Core areas are defined from a set of samples and are used to predict the frequency or likelihood of occurrence of an object or event. Spatial prediction typically translates from lower spatial dimensions to the same or higher dimensions. Spatial prediction methods may also be used to translate information from a higher order to a lower order. That is, to estimate point values from data collected or aggregated to area or lines. This may be affected by the modifiable areal unit problem, a common hazard in spatial estimation methods. Sampling. We control two main aspects of the sampling process. First, we may control the location of the samples. We may choose among different patterns in dispersing our samples. Sample number is the second main aspect of the sampling process we can control. There are times when we control neither the distribution nor the number of sampling points. This often occurs when we are working with found variables, for example, the distribution of illness in a population. Sampling patterns. A systematic sampling pattern is the simplest because samples are spaced uniformly at fixed x and y intervals. Systematic sampling has an advantage over other sampling patterns by way of ease in planning and description. Systematic sampling may suffer from a number of disadvantages. It is usually not the most statistically efficient sampling pattern because all areas receive the same sampling intensity. If there is more interest or variation in certain portions of the study area, this preference is not addressed by systematic sampling. Systematic sampling may introduce a bias, particularly if there are patterns in the measured variable that coincide with the sampling interval. Random sampling may avoid some, but not all, of the problems that affect systematic sampling. Random sampling entails selecting point locations based on random numbers. Random samples have an advantage over systematic samples in that they are unlikely to match any pattern in the landscape. Hence, the chances for biased sampling and inaccurate predictions are less likely. However, like systematic sampling, random sampling does nothing to distribute samples in areas of high variation. Cluster sampling is a technique that groups samples. Clusters are chosen by some random or systematic method. Reduced travel time is the primary advantage of cluster samples. Cluster sampling is often used in natural resource surveys that entail significant off-road travel because of the reduction in travel times. There are several variants of cluster sampling. Cluster centers may be located randomly or systematically. Samples within a cluster may also be placed at random or systematically around the cluster center. Adaptive sampling. Adaptive sampling is characterized by higher sampling densities where the feature of interest is more variable. Samples are more frequent in these areas and less frequent in flatter, less variable areas. Adaptive sampling greatly increases sampling efficiency because small-scale variation is better sampled. Largely, relatively homogeneous areas are well represented by a few samples. Adaptive sampling requires some method for estimating feature variation while in the field, or it requires repeat visits to the sampling areas. Sample density is adaptively increased in areas of high variation. Spatial interpolation methods. While methods vary, all combine the sampled values and positions to estimate values at unmeasured locations. Different interpolation methods will often produce different results. This is due to the differences in the mathematical functions and number of data points used when estimating values for the unsampled locations. Accuracy is often judged by the difference between the measured and interpolated values at a number of withheld sample points. Interpolation methods may produce one or more of a number of different output types. Interpolation is usually used to estimate values for a raster data layer. Other methods produce contour lines, more generally known as isolines, lines of uniform value. At least one interpolation method defines polygon boundaries. Nearest neighbor interpolation. Nearest neighbor interpolation, also known as Thessian polygon interpolation, assigns a value for any unsampled location that is equal to the value found at the nearest sample location. The nearest neighbor interpolator defines a set of polygons known as Thessian polygons. All locations within a given Thessian polygon have an identical value. Thessian polygons provide an exact interpolator. This means the interpolated surface equals the sampled values at each sample point. An independent error message is required if we are to obtain a good estimate of interpolation accuracy. Accuracy estimates may be obtained with a withheld sample technique. Fixed radius local averaging. Fixed radius interpolation is more complex than nearest neighbor interpolation, but less complex than most other interpolation methods. In a fixed radius interpolation, a raster grid is specified in a region of interest. Cell values are estimated based on the average of nearby samples. The samples used to calculate a cell value depend on a search radius. The search radius defines the size of a circle that is centered on each cell. Points that fall within the circle are averaged. Those outside the circle are ignored. The fixed radius interpolator tends to smooth the sample data. The search radius affects the values and shape of the interpolated surface. Too small a search radius results in many empty cells, with no data or null values. Too large a search radius may smooth the data too much. Fixed radius interpolators are not exact interpolators because they may average several points in the vicinity of a sample. And so, they are unlikely to place the measured value at sample points in the interpolated surface. Inverse distance weighted interpolation. The inverse distance weighted, or IDW, interpolator estimates the value at unknown points using the sampled values and distance to nearby known points. The weight of each sample point is an inverse proportion to the distance. The farther away the point, the less weight the point has in helping to find the value at an unsampled location. Each measured sample value is weighted by the inverse of the distance from the unknown interpolated location. These weighted values are added. The result is divided by the sum of the weights to scale the weights to the measurement units. IDW is an exact interpolator. Interpolated values are equal to the sampled values at each sampled point. The contribution from the nearby sample point dwarfs the contributions from all other points. Inverse distance weighting results in smooth interpolated surfaces. The values do not jump discontinuously at edges, as occurs with Thessian polygons, and sometimes with fixed radius interpolation. Splines. A spline is a flexible ruler that was commonly used by draftsmen to create smooth curves through a set of points. Mathematical spline functions, also referred to as splines, are used to interpolate along a smooth curve. These functions serve the same purpose as the flexible ruler in that they force a smooth line to pass through a desired set of points. Spline functions are constructed from a set of joined polynomial functions. Polynomial functions are fit to short segments. Splines are typically first, second, or third order, corresponding to the maximum exponent in the equation used to fit each segment. Segments meet at knots or join points. Typically, spline functions give exact interpolation. The splines pass through the sample points and show a smooth transition. Spatial prediction. Spatial predictions are based on mathematical models, often built via a statistical process. These statistically based models use coordinate location and measured or observed independent variables to predict values for important but unknown dependent variables. Spatial prediction is different from interpolation because it uses a statistical fitting process rather than a predefined algorithm, and because spatial prediction uses independent variables as well as coordinate locations to estimate unknown variables. Spatial predictions are a special case of general predictive modeling, the focus of applied statistics. While there are many types of spatial prediction, we will be restricted to predicting continuous spatial variables. These variables are conceptualized as spatial fields that they may be observed at any point across a spatial domain, are measured on an interval ratio scale, and typically have values that vary in concert. That is, they are spatially correlated. Spatial prediction may be considered more general than interpolation. Both methods are used to estimate values of a target variable at unknown locations. Spatial prediction usually incorporates additional variables. Prediction methods often address the presence of spatial autocorrelation. Spatial autocorrelation is the tendency of nearby objects to vary in concert. Explanations of this common condition often refer to the observation of Waldo Toppler, that everything in the universe is related to everything else, but closer things are more related. Correlations may be strong in one region, but poor in another, or positive in one area and negative in another. In addition to spatial autocorrelation, variables may show cross-correlation between different variables, the tendency for two variables to change in concert. Negative cross-correlation occurs when variables change in the opposite sense. Areas with high values for one variable are low for the other. The Moran's 1 statistic is an established measure of spatial correlation. Moran's 1 values approach a value of positive 1 in areas of positive spatial correlation. Moran's 1 approaches negative 1 when values are anti-correlated. There are many other local indices of spatial autocorrelation, or LISA, including Gary C, or the G of GETIS, and ORD, and they perform in a manner similar to Moran's 1. Spatial regression. Spatial regression and other statistically based prediction methods typically use observations of dependent variables, other independent variables, and sample coordinates to develop the prediction equations. Trend surface and simple spatial regression. Trend surface prediction is a type of spatial regression that involves fitting a statistical model or trend surface through the measured points. The surface is typically a polynomial in the x and y coordinate system. Trend surfaces are not exact predictors in that the surface typically does not pass through the measured points. This means that there is an error at each sample location, measured as the difference between the interpolated surface and the measurement. Trend surfaces are often among the most accurate methods when fitting smoothly varying surfaces, such as mean daily temperature over large areas. Trend surfaces typically do not have the bullseye artifact due to excessive local influence in inverse distance weighted interpolators. Trend surface methods typically do not perform well when there is a highly convoluted surface. Kriging and co-kriging. Kriging is a statistically based estimator of spatial variables. It differs from the trend surface approach in that predictions are based on regionalized variable theory, which includes three main components. The first component in the Kriging model is the spatial trend, an increase or decrease in a variable that depends on direction. The second component describes the local spatial autocorrelation, that is, the tendency for points near each other to have similar values. The third component in the prediction is random stochastic variation. These three components are combined in a mathematical model to develop an estimation function. Much like inverse distance weighted interpolators, weights in Kriging are used with measured sample variables to estimate variables' values at unknown locations. Kriging methods are the centerpiece of geostatistics. Geostatistics was initially developed in the early 1900s by D.J. Krieg and George Mathurin for use in mining. Krieg and Mathurin sought to develop estimators that would incorporate trends, autocorrelation, and stochastic variation, and also provide some estimate of the local variance in the predicted variable. Kriging uses the concept of a lag distance. The lag distance for a pair of points is the distance between them. Lag distances often are applied with an associated lag tolerance. A lag tolerance defines a small range that is close enough to a lag distance. The lag tolerance defines when distances are similar enough to be grouped in spatial covariance calculations. For example, we might set a tolerance for h of 10 units. Any pair of points between 102 and 122 units apart are used to calculate an index of spatial covariance for the lag distance h equals 112. Geostatistical prediction uses the key concept of semivariance to represent spatial covariance. A semivariance is the variance based on nearby samples. The semivariance at a given lag distance is a measure of spatial autocorrelation at that distance. High spatial autocorrelation means points near each other have similar z values. We may plot the semivariance over a range of lag distances, and this plot is known as a variogram or semivariogram. A variogram summarizes the spatial autocorrelation of a variable. The semivariance is usually small at small lag distances and increases to a plateau as the lag distance increases. The nugget is the initial semivariance when the autocorrelation is typically highest. The sill is the point at which the variogram levels off. This is the background variance, and may be thought of as the inherent variation when there is little autocorrelation. The range is the lag distance at which the sill is reached. The nugget, sill, and range will differ among spatial variables. A set of sample points is used to estimate the shape of a variogram. First, a set of lag distances are defined. Each distance signifies a given lag distance, plus or minus the lag tolerance. The semivariance is then calculated for each lag distance. A line may then be fit through the set of semivariance points, and the variogram estimated. This line is sometimes called the variogram model. Spatial prediction is among the most important applications of the variogram model. There are many variations and types of Kriging models, but the simplest and most commonly applied rely on the variogram to estimate optimal weights for prediction. Weights are optimal in the sense that they minimize the error in prediction, and they are unbiased given a specific data set and model. Kriging is similar to IDW interpolation in that a weighted average is calculated. However, Kriging uses the minimum variance method to calculate the weights, rather than applying some arbitrary and perhaps more imprecise weighting scheme as with the IDW. Co-Kriging is an extension of Kriging that includes the measurement of a separate, correlated variable at the sample locations in addition to the variable of interest. There may be an easily measured secondary variable that is to some extent related to the primary variable, but that is easier or less expensive to measure. For instance, temperature might be a primary variable and elevation a secondary variable. Co-Kriging exploits the covariance between the primary and secondary variables to improve the estimation of the primary variable. Co-Kriging is similar in motivation to Kriging in that a set of optimal weights is estimated, but with co-Kriging, there are weights for both the primary and secondary variables. Interpolation accuracy. How accurately does an interpolated surface match the real surface? And which interpolation method should be used? Accuracy is measured at assessment points, locations where we know both the true value and the estimated values for a variable. There are several metrics that are commonly used to characterize aggregate error, perhaps chief among them the root mean squared error. Error values are squared to remove the sign effect, and then the square root taken on the sum to return the measured unit scale, instead of a squared unit scale. Predictions either above or below the observed values are generally considered to be equally bad, and the error is averaged over all samples. However, squaring the errors magnifies the influence of outliers. extremely large positive or negative errors. So some argue that this is an overly pessimistic estimate of error, or at least when there are large outliers. The mean absolute error is an alternative error metric, less often used but less sensitive to outliers than the root mean square error. It substitutes the absolute value operation for the squaring square root operations, and so is less sensitive to outliers, but otherwise is quite similar to the root mean square error. Another accuracy metric is the mean bias error. The mean bias error measures the average bias in the predictions, the amount by which, on average, an estimated surface over or under predicts the true values. The mean bias error conveys useful information overall, but provides little information on the magnitude of individual errors and should be used in conjunction with a root mean square error, or preferably a mean absolute error. Overall measures of agreement between an estimated and true surface have been proposed, including Wilmot's Index of Agreement. Assessing the accuracy of an interpolated surface requires we collect both observed and predicted values at a set of points. There is a technique known variously as leave one out, bootstrapping, or cross-validation, which addresses both the undersampling and robust accuracy estimation requirements. Bootstrapping involves fitting the surface as many times as there are sample points, each time withholding one of the points. We fit the surface the first time, withholding the first point. We can then subtract the withheld measured value to the interpolated value and obtain one estimate of error. We then repeat this process for the rest of the sample points. For n samples, we fit the surface n times. Core area mapping. Core area mapping is another common and useful spatial analysis tool. A core area is a primary area of influence or activity for an organism, object, or resource of interest. Core area mapping typically involves identifying area features, such as polygons, raster areas, or volumes, from a set of point or line observations. Individual burglaries, for example, are recorded as point locations, perhaps tagged to the address or building where they occurred. These points may be used to define a polygon by one of several core area mapping techniques. This way, the core area is a higher dimensional spatial object or area that is defined from a set of lower dimensional objects, points or lines. This core area represents some central or important region where features occur frequently. For example, burglaries. Mean center and mean circle. The mean center and associated mean circle are perhaps the simplest and most obvious measure of a central location and a core area. The mean center is simply the average x and y coordinates of the sample points. Mean circles may be associated with the mean center to define a core area. The mean circles are defined by a radius measured from the mean center. The mean circle radius is commonly the distance to the farthest sample point. The average distance from the mean center to this set of sample points. Some measures of mean center may be biased by extreme points. Some multiple of the mean distance, or standard error, may be chosen based on statistical assumptions, or past experience. For example, if we assume the samples follow a random normal distribution, then a core area defined by a circle, approximately 1.8 times the standard error distance, should contain 68% of the data. Convex hulls. Convex hulls, also known as minimum convex polygons, are perhaps the simplest way to identify core areas with irregular shapes. A convex hull is the smallest polygon created by edges or lines that completely enclose a set of points and for which all exterior angles between edges are greater than or equal to 180 degrees. Convex hulls are often considered a natural bounding area for a set of points. However, convex hulls often ignore clustering in the data. We lose much of the information on density or frequency of occurrence in the interior region of the bounding polygon. Algorithms defining optimum concave polygons have been developed. Characteristic hull polygons. An alternative to convex hulls has been developed, known as characteristic hull polygons. A Delaunay triangulation is created among the sampled points, the same method as when developing a triangulated irregular network. A set of minimum spanning triangles is created, and the set of triangles winnowed to remove a largest area or longest perimeter subset. For example, the top 5% of polygons with the longest perimeter could be discarded, and the remaining shaded to represent a core area. This reduces the influence of distant points and allows for holes embedded within a core area. This is two advantages over convex hulls. Kernel mapping. Kernel mapping uses a set of sample locations to estimate a continuous density surface. Kernel mapping is widely applied because it is mathematically flexible, relatively easy to implement, may be robust to outliers, readily incorporates clustered samples, can represent irregular shaped core areas, and is often statistically based. Kernel mapping is based on a density distribution that is assumed for each sample point. These density distributions are placed over the sample plane, one for each observation point, and vertically added to determine the composite density from the sample. This composite density may be used to identify a core area, selecting the densest areas first. Density distributions typically are not squares or other geometric features, but rather symmetric shapes such as parabolas, Gaussian curves, or otherwise smoothly varying surfaces about a center point. Many functional forms can be used to represent the kernel densities. Typically, these shapes are bumps, in that they smoothly rise to a peak and then descend to near zero. Different forms of the kernel density function may have characteristic shapes, how fast they reach the peak, how pointed the peak becomes, and how quickly they return to values near zero at points more distant from the peak. A bandwidth parameter that controls the shape of the individual and hence composite density distributions. Narrower bandwidths result in higher and narrower peaks. We often choose bandwidth parameters, symbolized by h, that define the spread or width of the individual density distributions. Kernel mapping is generally a three-step process. First, collect samples and the concomitant coordinate locations. Second, choose a kernel density function. Third, choose a bandwidth, h. Apply the kernel density distribution and sum across each sample area to achieve the composite estimate of density. While the choice of bandwidth affects the results, there is no uniformly best method to select the appropriate value for h. Core area delineation is a primary use for estimated density distributions. As expected, the identified core areas are dependent on the selected bandwidth. Time geographic density estimation. Density estimators have been developed for space utilization by moving objects, typically animals for home range analysis, although sometimes other objects. An object may be observed periodically through space, for example, when a GNSS is attached to a migrating penguin, and the position relayed to a base station. These positions are often called control points because they establish the location of the tracked object at a fixed point in time. This sequence of control points defines a path. While locations between observations cannot be precisely determined, the control points constrain where the penguin might have been, because there is an upper limit on how fast the bird can travel. We may establish a maximum velocity, either from previous observations, from the current tracking effort, or from theoretical limits. The time geographic density estimation, TGDE, combines a sequential set of control points with knowledge about maximum velocity to estimate spatial occurrence probabilities. Time geographic density estimation depends on the concept of a geoellipse between 2 points. A time geographic estimate of space use is a composite of many observations. An object is estimated to have been contained within an ellipse given 2 subsequent control points. Longer time intervals between observations result in larger ellipses. As the interpoint distance approaches the maximum set by the maximum velocity, v, the ellipses become longer and narrower and reduce to a line when the points are spaced at the maximum possible distance. Conversely, the ellipses approach circles when the time interval between points is long, but the observed distance between points is small. This occurs when the object has not moved much, relative to how far it might have moved in the time interval between observations. GIS Fundamentals, Section 12, Spatial Estimation, Section Summary. Interpolation and spatial prediction allow us to estimate values at locations where they have not been measured. These methods are commonly used because our budgets are limited, samples may be lost or found wanting, or because time has passed since data collection. We may also interpolate when converting between data models. For example, when calculating a raster grid from a set of contour lines, or when resampling a raster grid to a finer resolution. Spatial prediction involves collecting samples at known locations and using rules and equations to assign values at unsampled locations. There are many ways to distribute a sample, including a random selection of sample locations, a systematic pattern, clustering samples, adaptive sampling, or a combination of these. The sampling regime should consider the cost of travel and collecting samples, as well as the nature of the spatial variability of the target feature and the intended use of the interpolated surface. Sample values are combined with sample locations to estimate or predict values at unsampled locations. There are many spatial prediction methods, but the most common are Thessian, nearest neighbor polygon, local averaging, or fixed radius, inverse distance weighted, trend surface, and Kriging interpolation. Each of these methods has advantages and disadvantages relative to each other, and there is no method that is uniformly best. Each method should be tested for the variables of interest under conditions in the study area of interest. The best tests involve comparisons of interpolator estimates against withheld sample points. Measures of core area are commonly identified from spatially distributed observations. This form of prediction identifies regions of high probability for an object or event. Mean center or mean circle are simple measures. A convex hull, defined as the minimum area polygon encompassing all points and with convex exterior angles, is commonly applied. More sophisticated measures include kernel mapping, based on centering scaled distribution functions over each observation and vertically summing the distribution functions.